Today, I want to tell you a fantastic story from the world of mathematics. It's about a problem that seems super simple on the surface, but it actually stumped some of the brightest minds for decades. And the solution? Well, it came from a really clever change in perspective, a local global trick that finally cracked the code.
All right, so here's how we're going to break this down. First, we'll get into the puzzle itself. Then we'll look at the old tools mathematicians had that just weren't cutting it. After that, we'll get to the breakthrough idea that changed everything, which leads us to the final answer and, what it all really means. So we're going to start with an idea you probably ran into back in school, just connecting the dots on a graph. But as you're about to see, there's a surprisingly deep and tricky problem hiding just underneath the surface. I mean, really think about it. If you've got a bunch of data points, what's the absolute best way to draw one single smooth line that passes through every single one? And this isn't just some abstract math puzzle, right? This is at the heart of engineering, data science, you name it. Well, it turns out there is a guaranteed mathematical way to do this. It's called Lagrange interpolation. And for any set of points you throw at it, it will spit out one and only one smooth curve that hits every single one of them. So, problem solved, yeah? Not quite. See, sometimes it works beautifully. If you place your starting points in a very specific, clever way, using what are called Chebyshev nodes, you get this gorgeous, predictable, totally stable curve. See how those waves are all even and contained? This is pretty much the ideal situation. But here's where the puzzle starts. This graph shows something called the Lebesgue function, which is basically a measure of the curve's instability. And whoa, look at those massive spikes. This means that even if you pick your points pretty well, the curve you draw between them can get incredibly wobbly. A tiny little change in your starting data could cause a huge, gigantic error in the final curve. So this wobbliness led the legendary mathematician Paul Erdős and his colleague Paul Turán to ask a really crucial question. What's the minimum amount of wobble you are guaranteed to get, even if you only look at a teeny tiny piece of the curve? And as he wrote himself back in 1993, they were pretty sure they knew the answer, but a proof felt, well, impossibly far away. Now, for a very long time, mathematicians had this really powerful set of tools to study these kinds of functions. The only problem was, this toolkit was designed for a totally different scale of problem. This toolkit is called global Bernstein theory. You can think of it like a set of universal laws of physics. They are incredibly powerful, they're super precise, but they only work for a special class of ideal functions, and only if you look at their behavior on a grand global scale. We're talking across the entire number line. So the big question is, why couldn't these powerful universal rules solve the very specific local problem that Erdős was wrestling with? It really just came down to a mismatch of scale. The global theory was designed to describe the entire universe, but the question was about what happens on a single city block. The everyday polynomials you get from connecting dots just didn't fit those ideal rules on a global scale. So the universal laws, they just weren't the right tool for this very local job. And this is where the story takes a fascinating turn, all thanks to a brilliant shift in perspective from the mathematician Terence Tao. He didn't invent a whole new universal law. He did something much cleverer. He adapted the old one. So instead of trying to force the problem to fit the old theory, Tao basically said, let's build a custom mathematical box around our little problem. The idea was to just look at the polynomial's behavior on that small local piece of the line and then analyze it inside this special, long, thin rectangle. It's like creating a controlled laboratory where a whole new, more specific set of rules can apply. And this image shows the core idea perfectly. By carefully defining how the function has to behave on the top, the bottom, and the sides of this rectangle, this new local Bernstein theory gave mathematicians the precise control they needed, right where it mattered, without having to worry about what was happening in the rest of the universe. So, armed with this new, super targeted tool, the answer to that decades-old question from Erdős and Turán was finally within reach. And there it is. Using his local Bernstein theory, Tao was able to prove that this formula, this is the minimum amount of instability, the minimum wobble you're guaranteed to find on any small interval. He confirmed what Erdős had suspected all along. This is the fundamental limit. You just can't do any better. And just like that, the result was in. The question was settled once and for all. A mathematical intuition that had been floating around for over half a century was now a proven fact. The answer was yes.
So, what's the big takeaway from all this? I mean, why is a story about wobbly polynomials and imaginary rectangles actually so important?
Well, this journey is just a perfect example of how science and math really push forward. It wasn't about some lightning bolt of pure, brand new invention. It was about thoughtfully taking a powerful classic idea and just adapting it. It was about zooming in from a global, universal perspective to a local, very specific one to finally solve a really stubborn puzzle. And that leaves us with a really fascinating thought, doesn't it? How many other huge, unsolved questions out there in every field of science aren't waiting for some brand new revolutionary theory, but are just one clever change of perspective, one local trick away from being solved?